Thank you, Eric. Good morning from New York, everyone. My pleasure to be here with you today to share some interesting insights on applied data science and machine intelligence. Thank you, Eric, and thank you to the Bern University for the kind invitation. Let me know if you can see my screen.
Yes.
Yes? Okay, great. So what we're going to talk today in the next half hour or so is a quick introduction to AI. I'm going to go quickly through those slides because I understand that most of you are familiar with the concepts, but then I will jump to how we use exploratory data analysis and different tools in order to work with highly unbalanced data sets from the financial sector. And part C will be building a model and deploying to production, different ways that you can do that. Before I continue, I would like to put a lot of emphasis in what Pablo just said a few times, the importance of working with subject matter experts at any stage of the implementation of a machine learning or data science project. This is critical for understanding the data, understanding the business requirement, and also ensure adoption of your solution. So that's very important. Thank you, Pablo, for making emphasis on that. And one more thing before we continue, I'm here today representing myself, not my employers. So just to make sure that this is based on my knowledge and prior experience. Before I continue with the next slide, I want to also emphasize how important it is for this type of work that you say a story, you tell a story. So when you try to present, especially to upper management, your work, or when you try to make a proposal about why something will be useful to your client or your manager, it's important to frame it in a way that it is a story that is easily understood. You should not make the assumption that people know what you know. It needs to speak to their language. So it's critical to understand what you're working with. It's critical to understand the requirements, and it's equally critical to present in a way so it is a story. And that's what I'm doing here with my presentation. I'm going to just start with the general information about AI. I'm going to go very quickly through the slides. So we know what artificial intelligence is, and we know how it's successful in the last few years. It's composed of machine learning, which is a subset where we employ algorithms that reprogram themselves based on the data. We feed them to the data, and then we create a program. And deep learning is another subset where we use neural networks and different topologies and architectures of neural networks to answer even more complex problems. It's been around for a long time, as you know. Now it's very practical because there's a lot of research that has taken place, practical research. We have a lot of storage, a lot of low computing capabilities. So now it is practical to use in business setting. Major categories of machine learning: supervised, unsupervised, reinforcement, and we can have a mix of those. So in a business problem, you can have, for instance, unsupervised learning to cluster your data to gain some insights, and then you can go into supervised for certain parts of the data where you have the output. So you can have a mix of different categories. Typically, we use one or two, typically just one, for a problem. And the big advantage in my mind is that we can build solutions much faster for complex problems because we actually need to choose the right algorithms, to choose the right parameters, to have enough data, quality data, and then by fitting the algorithm, we create the program. We don't have to write many complex rules to create the program. Deep learning is more complex, as you know. With neural networks, it's harder to explain. So it is mostly prevalent in research and technology companies. It's now starting the last couple of years or so to make its, presence into enterprise, especially traditional companies. Of course, smaller companies, startups, they employ this kind of techniques. But one of the challenges in the use case I'm going to work on and go through today is explainability. It's harder to explain the mathematics behind a deep learning architecture, but it's easy to prove that it works. So in the financial sector, where we have a lot of regulatory mandates, it becomes a de facto that it produces results. So this kind of agencies are a little bit easier to accept this type of techniques. NLP that Cortical is working on is one of experts, big experts in the area. Is proven to work very well. So even though it's complex internally, it is accepted and is being accepted more by regulatory agencies. So we're going to focus on our use case in finance markets, real estate and insurance. We have a lot of applications already for AI, for prediction, for security and fraud. We're going to talk about fraud detection today in our use case, risk management, news analysis, you name it. Now, this may seem different, but in a business setting, you may have a combination of those approaches in order to answer some of the questions. Why is our use case very important? It's because fraud is rising and it's very, very costly. It costs billions of dollars between 2017 and 2020. It's been up, especially credit card fraud that we're going to talk about. It's easy for fraudsters to get your personal private information at low cost. And also they can use AI in order to understand deficiencies in a credit card company or a bank or another financial institution and try to do something that will be fraudulent. The key benefit, as we know, is time. I was working for Citigroup a few years ago, where I was responsible for anti-money laundering, the program transformation. And I know by experience that it was very challenging. It is very challenging because you have so many cases to work with. So the use of AI to understand which cases are likely to be fraudulent is important because it reduces labor costs. And the labor cost for this specific area, anti-money laundering, is in the billions of dollars just to process the cases. And most of them are false positives. They're not real fraud. The main challenge is highly unbalanced data sets because most of the transactions are good transactions. The fraudulent transactions are a very small part of what we see in this type of data sets. Like the data set we're going to be looking at through this in this talk has about 500,000 transactions. Of those, only 711 are fraudulent and the other are good. So we have great imbalances. And therefore, in order to work with this type of problem, we need to do quite a bit of exploratory data analysis, a lot of pre-processing, and of course, try to balance the data set in order to make a good use of the model and have a model that can produce usable results. I would like to make a point that you can build a model that has very high performance metrics, but then it's not usable because it's not really predicting what we wanted to predict. So in this case, with highly unbalanced data, if you look at the accuracy of your model may be 99%, but you want to predict the 1% of the cases or 1 in 1,000 of the cases that will be fraudulent. So the accuracy as a measure is not necessarily something that's important for the usability and practicality of this type of model. So we have less than 1% in one class and over 99% in the other class, and that's a big challenge for machine learning as we apply it to fraud detection or this type of unbalanced data sets. Let's look at the pipeline. This is a typical pipeline for machine learning problems. Quite a bit of exploratory data analysis and pre-processing, visualizations, understanding the statistical measures of our data, imputation of missing variables, and shortlisting the important features. Now you can see which features are important at the early stage of the process, where you understand the business and you understand the data elements in your data set, and something that's totally irrelevant of the problem you're trying to solve, you can remove those. But what's very important is to go back and forth with SMEs and make sure that there are no changes to the data. Oftentimes, the data goes through certain pipelines before it gets to you to do this data science or machine learning AI problem. So you need to understand what they did. You need to understand if they have upper bounds to the data and they already transform it in some way, so that you can take appropriate measures through your future engineering transformation of and scaling to make sure it accurately represents the business. And then, of course, you go into modeling. You can use different algorithms, tuning of hyperparameters, and you can also use ensembling algorithms to improve the performance of the model. For this specific use case, as we start our exploratory analysis, it's always important to understand what kind of data we work with. So in this case, because it's private information in this data, the data set before we start has been converted. The features which are titled as V1, V2, represent different measures such as the location, the name of the person who does, or the transaction if it's available, the credit card numbers, etc., etc. So this has been already converted in order to mask information that is of private concern. And of course, we have the time in our data set, which shows when we start actually measuring the transactions that take place after the beginning of time. Basic measures to understand the statistical. And we can see right away from by looking at the statistics that the average for fraudulent transaction time is around 84 with a standard deviation 248. And in normal transactions, the average is similar to that, and deviation is similar to 50. However, we see the difference in the ranges. The minimum transaction in fraudulent was 0 because it was rejected. It was understood by the credit card company that it's fraudulent. The maximum transaction is low for our data set, whereas in normal transactions it's much higher. So we start understanding what the data means, what data we work with. This is important for the later part of the process, because when you build a solution for actual business use, practical business use, you don't just stop at the model development that gives you good metrics and you just deploy it. You have to wrap the model and the final solution around some rules, which may create some bounds with respect to what the model predicts. So in other words, if the model predicts that a transaction is fraudulent at a location that we happen to not have any activity or presence, then there may be some other what-if scenarios that you're going to present the end user with. Because the model may predict, but maybe something in the data through data drift got changed, which created an unrealistic prediction. So it's important to understand the data so you can create rules later on. Of course, a lot of exploratory analysis with visuals, depending on what type of information you want to explore. There are different types of visualizations. There are libraries in Python and other languages that you can use to do statistical profiling. So you can understand the data spread, the quality, relationships, and another type of data understanding that you can go through. One important point to keep in mind is that sometimes you do a lot of exploratory analysis, which is not really useful. You still need to do it. Maybe the results are not useful with respect to, let's say, correlations. In that case, you don't present it to management. It doesn't really tell a story. So you still have to go through that to understand what is going on, but you need to minimize what you are presenting to your client or your manager in order to actually tell a story, something that's useful. So through that exploratory analysis, we can see what data tell us, and then we can continue, for instance, because this fraud detection with location. We can create visuals easily in different programming languages or using different tools that will show us heat maps of those transactions. So the fraudulent transactions will show higher in areas that you have a lot. So for instance, you can use this information as you complete your solution to show that if a prediction that a transaction by the same credit card is taking place at a location that's totally irrelevant to the last 5 or 10 transactions, then maybe that prediction is not totally accurate and we need to put some warning to the end user. That's just an example of how we can use data points to measure, as a measure to evaluate model predictions and adjust results in deployment. Now, other things we can do with exploratory correlations. In this case, we don't see a lot of correlations. We can see time. We can plot against time to see if there is important information about when those transactions take place. We can do our scatter plots and see, for instance, our conclusion that there's less number of outliers in normal. And I'm sorry, this reverse, the red, this one is fraudulent. So we can see how the different type into the two classes of transactions that we have look like. And then we prepare the model for machine learning, the data for machine learning. In order to do that, of course, we need to work with outliers. We need to scale it in order to address skewness in the data, handle the class imbalance, reduce dimensionality, and then split the data for training. There are many techniques to do dimensionality reduction. Of course, some of the data which is not relevant, you do it manually at the beginning before you get to the stage. But then you can use different techniques such as TSNE in order to visualize your classes and also reduce the dimensions. And with respect to handling class imbalance, which is the major theme of our talk, you can use different techniques such as oversampling, undersampling, and the small algorithms in order to actually handle class imbalance and bring your data through scaling into similar measures for training your model. The next steps, as we prepare and deploy this, is we can use stratified split to take a good representative part of the populations of fraud transactions and normal transactions. And then we apply models to classify whether a certain transaction done at a particular time is fraudulent or genuine. It is important as we go through this to understand what kind of problem we deal with. This is a binary classification, yes, no, the transaction is fraudulent or not. I see in practice that sometimes data scientists, they go into one direction, they don't fully understand the problem, and then they work on a different type of problem. So we need to fully understand what it is and make sure that the algorithms that we select and the parameters that we tune those algorithms with are actually applicable for a specific problem. Something we should keep in mind that very high accuracy is not really important for this type of problems. So we should look at other measures such as F1 score, recall, and ROC curves in order to make sure that our solution has good performance metrics from a statistical perspective. For this specific application, I use machine learning algorithms. Again, I said we can go into deep learning, but sometimes machine learning works fairly well. You all are familiar with one of the very well-performing algorithms, random forest. It's hard to explain when you go to present your solution. It's easy to actually implement once the data is at that point by just calling a few functions and calling fit to train the model and then run the predictions. Again, all this code needs to be wrapped into a deployable application that's easy for the end user to utilize. Of course, we need to look at the metrics, confusion metrics with different kind of measures. For this specific implementation, I tried different algorithms and there are different results, like for the random forest that we mentioned, about the accuracy, AUC, precision recall, and F1. You can get this automatically, as you know, from the libraries. And of course, you don't do this with one model. You do it with multiple models, and then you compare the results and see which one performs best for your deployment. So what's next after you build a model and you tune it, and you make sure that it has good performance metrics? You need to make sure that the insights gain are based on an applicable amount of data. In our specific data set, the transactions are over a short period. Therefore, if we don't have enough data, we need to go back to the data providers and get more data in order to have a better trained model. We need to make sure that we look at feature importance and do feature engineering to improve the model even further. And also, we need to look at additional approaches such as deep learning. We need to use multiple statistical metrics in order to determine which is the best predictor and eliminate others. Field validation is extremely important. So you need to make sure that this works with real data in actually the business environment where new information comes in. And then you probably need to retrain it and tune it further in the production pipeline. So we're going to part 3. The typical ML process and how we deploy to production. So the typical ML, I already mentioned this, but I'm going to go over. We need to look at the big picture. How do we actually build something and how it fits in the overall business environment that they're going to be using this. We look at the data, visualize and insights, prepare for the training, select the model training, fine-tune it, and present a solution, and then monitor as you launch and maintain the system. So this is not, as you know, traditional programming where you have a solution, you have a program with the different rules and you deploy it. This is based on probabilistic and statistical theories. Therefore, we have model drift and data drift, and of course, we need to monitor and maintain it. If we employ CI/CD process in the pipeline and automatic alerts when we have this kind of situations, the data changes or the model's behavior is less than expected, then we can automate this type of process of retraining and tuning. How do you deploy to production? You can use a lot of environments which are available. For this example, we're looking at AWS, where you can have your data on storage in AWS S3 buckets, and then you can do this whole process that we discussed through different services that are available in AWS. Equally, we have the other environments, major players in Azure and Google Play, which offer a lot of capabilities. So you can have the whole solution built, customized, and deployed within a cloud service provider. Of course, when you create a model, you create an endpoint where the predictive capability is, and you call that from the UI that you're building in order to make it easier for the end user. Typical high-level architecture, you can use the built-in algorithms. Of course, these cloud services do not support all algorithms that are out there. So you can build your solution using scikit-learn if you use machine learning or any of the other popular packages. But then when you go to deploy, you may see that the specific algorithm that you implement with is not available. So you may have to make some changes along the way and adjust your solution if you were to deploy it in this type of cloud environment. And then you have different visualizations, such as QuickSight in AWS to work with visualizing the solution and creating the user experience. I'm running out of time, so I'm going to go a little bit faster, just a few more slides. This is an example of an architecture of how we can actually combine our repository in GitHub and different services in the cloud environment in order to build a solution, have different jobs that can run. So you can have different models that can be deployed at the time and measure how they work in the real environment. And you can route requests from different users, different offices that use this type of solution and measure how they actually work. And then you can train things in the background and redeploy and improve. And another architecture diagram here for real-time anomaly detection, because for fraud detection, you don't want to review the cases after the fact. You want to prevent on the spot. So you can have your training code as a deployed Docker container and the inference as another container, where you can continuously train the model and improve it, of course, within certain bounds. So the model gets improved as the data comes in, and becomes better in real time and creates the inference. And this is my last slide. Why not use automated data science platforms in order to build your solution better? One platform that I have experience with is DSS from DATAIKU, which allows you to build the whole pipeline in a way that it improves time to deployment. So you can do all your data preparation, visualization through different recipes. You can pull visual recipes, which are pieces of code in the background, in order to do all this work instead of just typing code by yourself. And then you can deploy the model. It can work well with different cloud providers or in your own on-premise environment. So this type of solutions, they become more and more popular. There are others out there. They become more and more popular because they speed up the process of EDA, model development, deployment, and monitoring. Again, these platforms may not support all algorithms that are available as open source. So it's always, for completeness of your work, to keep in mind what is going on in the research, what's going on with practical solutions that are available as open source. And sometimes you may need to do a mix of different tools and techniques in order to create the best solution. For these platforms, you can write your own code. You don't have to use visual recipes. So, for instance, in DSS, DATAIKU'S DSS, you can pull some ready recipes in order to manipulate the data, in order to train, and then you can inject your own code in order to make it more complete. Of course, cloud environment will help you, especially when you deal with large data sets, and computing requirements are of importance because you can spin off a machine with high power at a lower cost for the time that you need to train the model, and then shut it down, and then create your endpoint for deployment, which will be at a lower cost, and you can speed up your deployment, development and deployment process, using those kind of services. So that's it from me. Thank you very much for your attention. It was a pleasure to give this presentation to you. I hope you found it useful. And please feel free to reach out via LinkedIn to connect and stay in touch.